Alrighty guys, so what I'm going to do is answer some questions from the, let me move this a little bit, yikes, from the chapter review for our block. I had said if you had questions to put it in the chat, and so the numbers I had were 15, 16, 17, 18, and 19. So we're going to go ahead and do that. And I made a printout of this, but I don't know, the tables and things come out a little bit. It's not really the table, I think it's the camera. It doesn't like grit, well, it's far away, but anyway, so we're going to start with number 15. And 15 is hard because they want you to sketch a possible graph. So there are many possible graphs. So let me just get that out of the way, and I'll make this bigger in a minute. Sketch a possible graph of a function g. So I'm just going to note here real quick, we've got an interval from -3 to 2. I'm going to note the characteristics. G prime of -1 does not exist. So what I'm thinking here is that either the slope is really steep at -1 of the graph of G, or, you know, maybe there's a break in the graph, something like that. G prime of 1 is 0, and the second derivative is less than 0 for all x. So what this means here is that my graph is going to be concave down for all x, okay, where the second derivative exists. The second derivative is not going to exist if the first derivative doesn't exist. So I'm getting little clues in here. But again, I can't draw, so this is going to be no easy task. So let's make this big. And these are the characteristics of the function g that they want me to graph. So, you know, here's 1, 2, 3, 1, 2. Okay, there's my window. All right, and what I know is that g of -1 does not exist, and that g prime of 1 is equal to 0. So what this implies to me is that I'm going to have a bump, right, on the graph of g. This implies that my graph of g is going to be concave down. And this one right here is telling me that at -1, the derivative is not going to exist. So maybe it's some kind of a, let's see, do I have a pencil? I don't know if I have a pencil in my cup. I have all these colored markers. I have like this menagerie of marker colors. Ooh, but I don't have a pencil. Oh well. So maybe I have a break right here at -1, or perhaps I have this really steep sort of line or something like that. All right, so let me make a new grid. That's terrible, but anyway. All right, the other thing I know is that this is going to have to be concave down everywhere the second derivative exists. The second derivative is going to exist everywhere except for where the first derivative doesn't exist. So g prime, so at x equals 1 is going to be a problem on this graph because the derivative is not going to exist there. So, you know, you could make a break in the graph of g. You could give it a super steep slope so that if you drew a tangent line to that, the derivative wouldn't exist at that point. It might even have a corner there. All right, the graph may come, so remember, this could be a myriad of different graphs, and none of them would be wrong. But, you know, I'm going to probably make a corner here. And g prime of 1 is 0, so I know at 1 I have to have a bump. All right, and g prime, so maybe my graph looks something like this. All right, my derivative would not exist at -1. The derivative at 1 is 0. If I draw a tangent line to my graph, it would be 0. And my second derivative is down everywhere, or sorry, concave down, meaning that the function, my second derivative is negative, meaning that the graph is concave down. So maybe my graph would look more like this. You know, maybe it's concave down and I have this very sharp corner where the derivative doesn't exist, which means the second derivative wouldn't exist. It could look like that. It could look like something like, so we'll call this -1 here. It could look something like this. 1, 2. real bad again. It could look something like that. So don't sweat that. They're not going to ask you to draw something like that on your AB exam. They would have you do a quick sketch of f prime given f or something like that, but they're not going to have you do anything. It's just thought-provoking, and it makes you think about all the possibilities that could happen in this particular scenario. So it's just an exercise to make you think. It's a good exercise, but it's tedious because it's hard to, you know exactly which graph it is. There's many graphs that would fit this criteria. So don't worry yourself about that one too much. All right, let's look at number 16. A meat and potatoes kind of problem. Okay, so you are starting at time equals 0 and objects moving along the x-axis. Position function is given, okay? They want you to complete the table. No problem. So I'm just gonna put this right here because that's what I wanted this printout for, was for the table. And what you were expected to do is to put your position function in your calculator. So let me make this big again. Oh, this lines is just awful. It's awful. That's a little better, I guess. Okay, so they wanted you to put your function in. Now, that's the position function, the one that's already in y1. And y2, if I want velocity, that's a math 8, right? The derivative represents velocity, and I want it over the entire domain. So over here, I'm going to put in x. And then I want acceleration, which is the second derivative of position or the first derivative of velocity. So what I'm going to do here is I'm going to do math 8, okay, with respect to x, vars right arrow 1, 2. In other words, I'm taking the derivative here of the derivative above it. This is the second derivative, or acceleration. And again, I want it over the entire domain because I want to see what's going on. Now, for the position part of the graph, that's easy. I'm plugging in every one of these numbers to see what the output is. So if I plug a 0, if I plug a 0 in for t, well, I'm going to have 0. Right? And if I plug a 1 in, I'm going to have 1 minus 2, which is negative 1, minus 6, which is negative 7. And if I plug a 2 in, 2 to the 4th is 16, so I better write this down. 16 minus 2 times 4, 2 squared, which is 8. So 16 minus 8 is 8, minus 6 times 2. So 8 minus 2 is negative, 8 minus 12 is negative 4. So that was an easy peasy part. Now the second ones, you're going to have to use your graphs, all right? So what I would do is I would shut off the graph of the original. So you just arrow over to the equal sign and press enter, and you see how this one up here is not highlighted anymore? That means I shut it off. And I'm going to shut off the second one too, because I'm just focusing on velocity, all right? And I'm going to hit the graph key, so that way I get just the velocity graph. And we'll wait an hour or so for that graph to come on up. There it is, okay? So what we want to know is, for velocity, what happens when t is equal to 0? Well, the velocity here should be negative 6. And so, you know, xt, right, same thing. So when x is 0, all you have to do is find this point right here. And you can use your table even. Okay, when t is 0, y is negative 6. So what I know is that my velocity is negative 6 here. Okay, what's the velocity when t is 1? Well, I can go to my table and I can see it's also negative 6. So I'm going to pop that on in there. Okay, and finally, what happens when t is 2? Well, when t is 2, the velocity is 18. So I'm just using the table feature on my calculator to get these numbers. You don't have a choice because you don't know how to take the derivatives yet and plug the numbers in at this point. I mean, you do, but you're in chapter 2, so technically you're not allowed to use them. So the easiest thing would be to do is to use the table on your calculator if this is a calculator problem. And then for acceleration, well, I don't want to look at this graph anymore, so I'm going to shut the second graph off, and I'm going to turn the third graph on, which represents my acceleration, and I'm going to hit the graph key and wait for that graph to come up. And I'm essentially going to do the same thing any day. My goodness. Here it comes. Okay, so now we have this little parabola, all right? And I want to know, what is the acceleration when t is equal to 0? Well, what I'm looking for is the y-coordinate, right? So again, I can do second table and go to my table. Maybe I didn't press the button. It's probably still... Okay, this calculator is getting on my last nerve. Here it is. Okay, so when t is 0, y is -4, so I'm going to throw a -4 in my table. When time is 1, well, my acceleration is 8. And when time is 2, my acceleration is 44. And that's it for number 16. Oh, no, there's a part B. Sorry. There's a part B. So in part B, it says, at time equals to 1, the object speed increasing or decreasing? Explain your answer. Okay, well, I'm going to look at time equals to 1, and the thing I'm going to look at is the difference between the acceleration and the velocity. Why? Well, because when velocity and acceleration have different signs, then what that means is that the speed is going to decrease. Okay? Really important. It doesn't matter if velocity is positive and acceleration is negative, or vice versa, the way that it is. If the signs are different between velocity and acceleration, then that implies that the object is decreasing in speed. So I would say that the object's decreasing because velocity and acceleration have or opposite signs at that point. At t equals 1. Okay, so I think 16 is done. Let's see, the next one was 17. Now 17, you're expected again to use your calculator. Okay, so I'm going to get rid of these graphs here. And what you're going to do is you're going to put the function part in, okay? And you're going to find the limit as x approaches the different numbers that are given here. So in the first one, and you got to be careful when you put these into the calculator, you need to use, especially if you have more than one term in the numerator, you need to put parentheses around them. And the denominator, since we have a radical, we don't need parentheses around it, okay? So what I'm going to do is I'm going to put parenthesis x squared plus x, plus x, in parentheses, divided by the square root of 4x squared plus x cubed, okay? And I'm going to hit the graph key. And here comes my graph. Now what I notice here, but it doesn't matter, so I'm just trying to push this camera really far down. I'm trying to find the limit as x approaches 0, so let's find some pretty colors. How about like, I don't know, these two colors, summer colors. And what I'm going to do is, you know, in order for the limit to exist, I have to come in from the left and the right. Well, the limit from the left as x approaches 0 from the left is like -1/2. And the limit as x approaches 0 from the right is +1/2. Since the limit from the left is not equal to the limit on the right, I would say that the limit does not exist. Okay? So for number 17a, oh my gosh, the cap doesn't want to come off. 17a, the limit does not exist. In 17b, I need to put that function in. So I'm going to do that, and I'm going to show you how I enter it. So in B, I've got my parentheses for my numerator. I have 1 minus parenthesis 1 divided by x, close the parenthesis, and close the parenthesis again. I've got outermost parentheses, and then I'm putting 1 over x in its own parentheses, divided by parenthesis 1 minus x, okay? And I'm going to hit the graph key, and we want to find the limit as x approaches 1 on this graph. Now, it's very clear, well, maybe not. Yeah, it's very clear here. I don't know, I kind of think it's not clear. Oh, wait a minute. Yeah, as x approaches 1, right? So as we come in from the left, this is wrong. I think his answer is wrong. If I remember, I think his answer was like, was it 1? Let me see. -1. Okay, this is wrong answer that he gave. Because as we come in from the left-hand side, well, the limit, the height is like 6 or something. I don't even know what that number is. Okay? As we come in from the right, the limit's approaching, well, all right, so let's see. It's approaching 0. It's approaching 0. The limit does not exist here. We've got an asymptote at 0, and so the limit does not exist. Hang on, I want to check something. This was, what was the function again? 1 minus 1 over x. Oh, I'm sorry, it was at 1. I was looking at the break in the graph. I was focused on 0. Yeah, it's still wrong. As x is approaching, oh yeah, I'm dumb. So this is the left side, but this is also the left of 1. Tricky problem. See, I missed that. As x is approaching 1 from the left, the height is -1. And as we approach 1 from the right, it's also -1. So he's right. The limit is -1. Sorry, I was just focused on that 0 for some reason, I guess from the last problem. Okay, next problem is x squared minus 3x plus 7 divided by x squared minus 9. And we want the limit as the graph approaches 2. So we want the limit right here when x is approaching 2. Well, if we come in from the left, the height looks like it's about, I don't know, a -1 maybe? Again, negative a half-ish. We come in from the left to 2, it's about a -1, I'm going to say. And if we come in from the right side of that point, it's also the same height. And so, again, I'm thinking it looks like -1 to me, or maybe a half, but I'm going to say it's -1, just to be easy. If he has a half in his answer, then, I mean, here's -1, so yeah, I would say it's -1, okay? So the limit for C is -1. And then finally, in the fourth one, oops, we have the sine of 2x divided by 3x. Nice little problem. And we're going to hit the graph key, and we're going to get the sine function. Okay, it's a double angle. And there's our beautiful function, and we want to investigate this thing as x is approaching 0. Well, let's see if I can trace 0, enter, and then I'm going to zoom in. I really want to zoom in around that point of interest. It looks like 0 to me. But I know it's not 0 because I know some things about this function. So it's telling me when x is 0, y is 0. You know what? Hold tight on this one because this is a special function. There's a function called the sine of x over x, and then it's got modifications. But the answer is 2/3. And when you learn some derivative rules later, you're going to see that 2/3, these numbers here, are going to come out of this. All right. So for right now, we'll get back to these type of problems later, but it's definitely 2/3, although the graph, let's see. Well, yeah, here it is. If we look at the table, I mean, 0.3031 is 0.666. Yeah, so it's not the same. So anyway, hold off on this one. This is a special class of functions, and we're going to study them in depth, so don't worry too much about that one. But he's got the correct answer there, 2/3. But any new calc student would probably be, oh, wait a minute, you guys are BC. What am I thinking? You guys should know how to find this derivative. Right? The rule of L'Hopital, right? Because the sign, if I plug a 0 in, I've got the sign of 0, 0 over 0, so that's an indeterminate form. That means I need to take the derivative of the top, so which is cosine of 2x times 2 over the derivative of the bottom is 3. Now if I plug the 0 in, that's perfect because the cosine of 0 is 1, and 1 times 2 is 2 over 3. L'Hopital's rule for you guys. Okay? But it does look, graphically speaking, that the limit is 0, but it's not. Graph or failure. So that was number, what number was that? 17. So now we have 18 and 19 to contend with. Okay, so since we've got a graph here, I'm just going to I'm going to move this over out of the way, and I'll just use my cursor to point. And if I need to write something, I will on the paper. So number 18, it says, let G be a function whose graph is shown below. So this is the graph of G. At what x is G not continuous? In other words, where there's going to be breaks or weirdness, right? Well, G is not going to be continuous at x is equal to -4. Why? Because the limit, the right-sided limit anyway, of this is not equal to the function evaluated at 4. So in other words, if I did a right-sided limit, the limit of this thing would be a 1, but the function f of -4 is 0. They're not equal, so it cannot be continuous, right? The next point would be at -2. So you always read a graph from left to right. Why? Well, the limit exists. The limit as we come in from the left is equal to the limit as we come in for the right. They have the same height of -1. The function is defined at x equals to -2, right? F of -2 is 3. However, the limit as x approaches -2 of this function is not equal to g of -2. They have to have the same height, and they don't, so it's not continuous at that point. The next one would be at 0. Again, same reason. If I take the limit from the left, it's -3. The limit from the right is +3. So the limit doesn't even exist. So I don't even need to go any further. But the function is defined. It's just not equal to the limit. So at 0, it doesn't work. At 1, again, the limit doesn't exist. The limit from the left is 4. The limit from the right is 2. They're different numbers. It doesn't exist. Done. The next one would be at 3. Again, the limit from the left is 0. The limit from the right is 2. I think that's 2. So therefore, the limit doesn't exist. And finally, at x is equal to 4, because the function is defined, however, the limit doesn't exist. The limit from the left exists, but there's no limit from the right, and they're not even the same as the output value of the function. So those would be the reasons why the function is discontinuous. In part B, they want the limit as x approaches -2. Well, we already said that. If we come in from the left, the height is -1. If we come in from the right, the height is -1. So the limit as x approaches -2 of this function g is -1. Now this right here means, so you notice these have as x approaches a number. This is as h approaches a number. So what they're asking you for is, what is the derivative of this function g when x is equal to -1? Okay, in other words, what's the slope of the tangent line to this graph at -1? Well, if I come down to -1 and I plot a point and draw a tangent line, my tangent line is going to coincide with the line this line segment that's right here. They're going to have the same slope, right? The derivative of a linear function is the slope of the linear function. They're the same. So all I need to do is choose 2 points on this graph here and compute the slope. Easy. I've got the point -1, -2. I guess I better write up here. Hang on. -1, -2 is 1 point, which is this convenient little point here. And if I want, I can use 0, -3. So I know the point's not, the point is defined here, but I'm using this point even though it doesn't exist right there. It's okay. And so the slope is going to be -3 minus a -2 over 0 minus a -1, which is -1 over 1 or -1. So the slope of this line is a beautiful, perfect -1. You probably could have eyeballed that and got that right. And here, the limit as x approaches 3 from the left, well, here's 3. And if we come in from the left, the limit is 0. That's the height of the graph as we come in from the left. And this here, part E, if you remember from last year, I teach the existence theorems all together. There's the intermediate value theorem, the extreme value theorem, the extreme, medium, I'm missing one, IVT, EVT, and MVT, mean value theorem. I teach those all together. So for right now, you can disregard this. I'm going to do the same thing again this year. I'm going to teach them all together. So we'll come back to these types of problems later on in the book. You wouldn't be tested on this right now. All right, so that was 18, and I think the last one that was asked was 19. This is a function f is defined by this rule. So here's the function. Our problem child is at x equals to 3. And it says, is f continuous at 3? And right away you just say no. Why not? Because 3 is the problem. The reason why this graph is in pieces is because it's a problem. Now you could look at the graph. You could graph the piecewise function. So remember to put it in pieces. I'm going to do the numerator. So x squared plus x minus 12, close the parentheses, divided by x minus 3, right? Now, I need a parenthesis around this whole shebang as well, because I have to put my argument in like it's being multiplied next to it. So I have to do parenthesis, x second math 2 cannot equal 3, and close my parenthesis, plus, now the next piece of the function is 0, argument, when x second math 1 equals 3. Okay, and I'm going to graph it to see how the graph comes out here. I'm probably going to have to adjust my window. I am. So I'm going to do a zoom 6, and that should do it. No, it's not going to do it. It's such a terrible calculator. But what I know from the top function is the piece on the top. It's really too bad. I'm going to have to find my other TI, my gray one, and use that one because that one's so much nicer. But, you know, this is clearly not a linear function. But I can factor this, right, to x plus 4 times x minus 3. It has a removable discontinuity. So if I'm thinking about that function, I'm going to have x plus 4 times x minus 3 over x minus 3. And when I remove that removable discontinuity, what I get is a nice linear function, which is just going to, it's going to go right over this line. So you're not going to see the hole or the break or whatever that's in it, okay? Now, f is going to equal to 0 at 3. All right, which, you know, you don't even see that. And in fact, if I look at my table here, 0, it's 4. Yeah, sure. Okay, so anyway, it's a little bit messed up, this function is. But, you know, is it continuous at 3? No. All right? because, and again, let me just see something here. So look, at 3 on the table, and I know this is hard to see. Let me just make it bigger. Whoa, there we go. Oh, that's much nicer. There we go. Okay, at x equals to 3, there's an error in the table, so no. But anyway, that's going to happen because we have a problem at x equals 3. Remember that the restriction is always the problem, all right? It says determine f prime of 0. Well, if I take the derivative of this thing, so, you know, if this is f, if I take the derivative of this piece here and then evaluate it at 0, it should be 1. Yeah, wait a minute, let's see. Let me look at the graph again. Yeah, it would be 1. Because so here's my graph, right? And if I evaluate the derivative at 0, that means what is the slope of the tangent line of this curve at x equals to 0. So if I put a little dot at 0 and draw a tangent line, it's going to have the same slope, all right? And from this graph key, you know, I could do second, draw 5 tangent at x equals to 0 if I wanted to. You're not going to see the tangent line because it's coincident, but you look at the equation of that tangent line and it's 1x plus 4. So what that means is that the slope of that line is 1. In part C, they want the derivative at x equals to 3. Well, the derivative at x equals to 3 is not going to exist. Why? Because we have a problem at 3. All right? When x equals 3, y equals 0. And it's not true. Y is 4 here, right? If you look at your table, we saw that a minute ago. Okay? When x is 0, y is 4. So technically speaking here, because there's a problem here, there's a hole in the graph. The derivative can't exist at that hole. You just can't see the hole, okay? So the derivative is not going to exist. So I hope that this helped those of you who had these questions. And if you have any more questions regarding what I talked about, please don't hesitate to let me know. I try to be at your service 24/7, and I'll get back with you and try and help you out a little bit more, okay? So have a great night, great weekend, and I'll see you the next time I see you. Monday, Tuesday, I don't know.